Welcome. In previous videos we have discussed how to process experiment data that we can use them as inverse modeling targets. We have also discussed how to set up pyrolysis reactions in the respective FDS input files. Alright, let's start with a brief overview over inverse modeling by comparing it to direct modeling. Direct modeling is relatively straightforward. We have some model and we provide it with parameters that we get from literature or the experiment. Then we run a simulation and get a result. This requires that we have all the necessary models and parameters. However, not all parameters may be easily obtained, if at all. A different approach would be that we start from the target that we want to reach, for example the experiment data. We are using the same model and we ask then the question, what parameters would we need to provide to the model to get to this result? It is important to note that the parameters that we get are effective parameters that are also model dependent. So, direct modeling, we know the input parameters and the model and ask what is the response. For the inverse modeling, we know the target and the model. We ask then what parameters do we need to put in to get as close as possible to the target. We start the process by generating a parameter set. It is provided to the model to run a simulation. Afterwards, the response is compared with our target data and we check if the convergence criteria are met. If this is not the case, the loop is run again until convergence is reached and we get our parameter set. The parameter sets are generated by some optimization algorithm. In our case, we are using the shuffled complex evolutionary algorithm that is provided from the Python package SpotPy. With template files, we can provide the parameter sets to our model, which is the Phi Dynamics simulator. The model will be run on some computer, preferably a supercomputer. With this, we can utilize many CPUs to run through all the parameter sets. Because during an inverse modeling process, we typically generate thousands of parameter sets, which means we need to run thousands of simulations. We also need to then provide the target data, which in our case is the processed microscale experiment data. To manage the overall process, we are using PROPTI. This is a generalized inverse modeling framework that we have developed. It is open source and freely available via GitHub. The links are in the video description. Important to note is PROPTI does not provide any optimization algorithms or anything like that. It is just handling the communication between all the different stakeholders. For example, PROPTI takes the parameter sets from the Optimiser and writes them into the simulation template files. On the supercomputer, it will then run the respective simulations. The simulation result is then provided to the Optimiser so that it can generate the new parameter sets. I believe it is important to provide a few words of caution. In the following section, I'm going to present an inverse modeling setup for the microscale simulations. I used the experiment data series that we created in an earlier video as target, which you see here on the right hand side. The fundamental idea of the next section is that the mass loss rate multiplied by the heat of combustion leads to the heat release rate. Thus, plotting both of them against the sample temperature should lead to overlapping plots. However, this may not necessarily be the case. In the setup here, we could observe that the algorithm was not able to find a parameter set that could reproduce the mass loss rate for the TGA experiments at 10 Kelvin per minute and simultaneously the heat release rate of the MCC experiments at 60 Kelvin per minute. This is what you see on the left hand side. The dashed line is the target that was supposed to be reached and the colorful lines are the responses from the simulation. It worked using the TGA experiments at 50 Kelvin per minute and the MCC at 60 Kelvin per minute. This is what you see here on the right hand side. In the literature it is reported that a shift could be observed when trying to plot mass loss rate and heat release rate together. Specifically here, where the authors report they observed heat release before mass loss was detected. To mitigate this issue, they shifted the data by a couple of Kelvin. As they point out, it was between 4 to 20 Kelvin, depending on the experiment. In the MCC, there is a pyrolysis chamber in which the sample is located and a combustion chamber above that. The presented idea is that the combustion chamber above the sample is operated at high temperature. From there, extra thermal energy is reaching the sample from the top. This may lead to a higher heating rate for the sample inside the crucible than what can be captured from the thermocouple below the sample. Just recently I found this article. Here the author does neither report the observation of a temperature shift nor methods to account for it. Having a look at the plot on the left hand side in figure 3, here it appears that the data series fit together as I would naively expect it. The mass loss rates are presented as the dotted lines and the heat release rates as the red solid lines. When you look at the temperature range between let's say 250 to 280 degrees Celsius, you see that the mass loss begins at lower temperatures than does the heat release. For now I have no idea what is the correct way, so to speak, and unfortunately I cannot provide you a solution. I am also not claiming that any of these presented articles are either wrong or correct. The goal is to emphasize that if you are interested in reproducing the procedure I am going to present here, you may want to be careful and possibly not use the MCC data series as target directly. I believe that integrating the heat release rate should be fine and could be used as a constant heat of combustion. Also, many people assume the heat of combustion to be constant to begin with. However, if you look on the right hand side, you can see there is a red dashed line which indicates the constant heat of combustion, and you see the red solid line which indicates that the heat of combustion may change. You could for instance think about some technical material which has some fire retardant properties. In this case, you may have substances mixed in that are releasing carbon dioxide at lower temperatures. In this case, the heat of combustion of the released gas mixture should change. We have also argued this in the discussion of the article preprint. However, this just opens another can of worms, and I'm not interested in dealing with that in this video. Just briefly, we have argued also in the discussion that one might be able to use multiple decomposition reactions that are only releasing either methane or carbon dioxide. Having these decomposition reactions overlap would provide a simple way for the model to change the composition of the released gas mixture. We tried this strategy out, and we have encapsulated the results in the parameter set that we submitted to the MacFP3 workshop. In total, we are using 4 decomposition reactions. 2 are releasing carbon dioxide, which is marked here in red, and 2 are releasing methane, which is marked here in blue. With these 4 reactions, the gas mixture changes depending on the material temperature. The goal of these videos is to document the process that we have used for our article. Still, I would like to use the opportunity to provide extra information that we have learned during the process and also afterwards. Anyway, let's get started to set up the inverse modeling process with PROPTI. Let's go back into the project directory to prepare the inverse modeling process. Into the project root, I have simply cloned the PROPTI Git repository. Furthermore, I have created a directory that will hold all the IMP runs that are conducted for the microscale experiments. In here are multiple directories. Their label contains the material of which we want to create a parameter set and also which experiment data we use as target. Since the concept for setting these IMP runs up is always the same, I will just focus here on the 02. In here is a directory with the same name as the one above, but it also has a L0 at the end. These L0, L1, L2 indicate limit adjustments that have been conducted during the inverse modeling process. This is not so important right now, but I will explain that later on. In this L0 directory are the files of the processed experiment data that we have created before, the FDS input file, which we have also discussed before, that will later become our template, and also a Python script that will serve as input for PROPTI. Here on the left we see the start of the PROPTI input file where I have already filled in a couple of lines. On the right hand side we see the FDS input file that we have used earlier to generate our first gas for the pyrolysis scheme, where we had positioned different decomposition reactions. For this inverse modeling process I would like to use 2 different targets simultaneously. At first I want to use the MCC to capture the heat release. Secondly, I want to use the TGA to capture the mass loss of the sample. I will set up now everything for the MCC simulation, and then afterwards we can simply add in everything that is related to the TGA simulation. To distinguish the individual simulations, we are using the character ID. Here I have defined the file name for our FDS input template that is related to the MCC. For the file itself, we just copy the FDS input file and then make the appropriate changes. Here's a value for the residue production. This we have calculated earlier in the video where we were discussing how to process the experiment data. Here in lines 25 to 27, I have set up the file names that hold our experiment data that will be used as targets for the inverse modeling. In lines 31 and 32, I have initialized data collection for the individual parameter sets. We have 2 different groups. In line 31, the list that is called set of parameters will contain the parameters that are changed by the Optimiser. In line 32 is the list for the environment parameters. These would typically contain information about the setup of the simulation itself. For example, you could put in here the different heating rates for our tests. However, in this case I did it in a different way. I have different templates that already contain the respective heating rates. You will see later on that we have some parameters that have dependencies. These dependencies require some helper parameters, and these helper parameters are also collected here in this environment parameters list. So I guess in this case the distinction is not as clear-cut anymore between the parameters to be optimized and parameters that set up the environment. This is a little bit convoluted, but I will explain this later on. We built our inverse modeling process in multiple steps. At first we define the parameters that we are interested in. These are the parameters that the Optimiser will adjust. Then some general information is provided for a specific simulation. Afterwards we need to define relationships between the target data and the model responses. All the information from above will be combined into a simulation setup. As a concept, I believe the simulation setups are relatively straightforward. Everything related to a specific experiment and a specific condition is a setup. So for example here, MCC at 60 Kelvin per minute and TGA at 50 Kelvin per minute. We will then collect the different simulation setups into a simulation setup set. This will then contain the TGA setup and the MCC setup. Finally, we need to provide some information for the Optimiser, which is essentially where is it supposed to run the simulations, which software is it supposed to use, or how many generations need to be run. I'm aware that this is a lot of information, so please feel free to ask questions in the comment section. Now let's define the optimization parameters. I would like to start with the parameters for the first decomposition reaction. In the beginning of the document we have imported PROPTI, and we will now make use of this to access different data objects. Specifically, we are looking into the parameter object. Each parameter needs to get a name. I have chosen here PMMA component 1 because it is the first reaction PMMA 1. And I added ref temp because I want to adjust the reference temperature. Next we need to define a sampling range between a maximum and minimum value. I started from the first gas and just added and subtracted 8 Kelvin. Therefore the minimum value is 375 degrees Celsius and the maximum 391. Now we need to connect the parameter within PROPTI with the FDS input file. For this I've copied the FDS input file to make it the template. We are simply using placeholders in the FDS input file to indicate where the parameter needs to be written. I take the placeholder I've defined in the PROPTI input file and copy it. Then I write it into the FDS template where I later want to have the parameter to be written. Note that we have the convention that the placeholders need to be wrapped with the hashtag or pound sign. This is only necessary in the template because PROPTI will add the hashtags on its own. Now our parameter will be added to the list of parameters that we have defined above. Next we will set up the pyrolysis range. This follows the same concept. We define a name, a placeholder, as well as a sampling range. And we have also written the respective placeholder to the template file. And finally, for the first reaction, we have set up the heat of reaction, so note that the heat of combustion has here changed to heat of reaction and the respective placeholder was added. This process will now be repeated until we have covered all 8 decomposition reactions. After all the decomposition reactions are set up, now let's have a look into the parameters with dependencies. As I said before, I would like to set up a gas mixture as surrogate fuel. The goal is to set up a mixture with an effective heat of combustion that matches the information we get from the MCC experiments. The components of this gas mixture I've taken from this article here. You find the links in the video description. The authors state here in the beginning that the solid PMMA will decompose into its monomer MMA. Afterwards, the MMA will further decompose into smaller molecules, which are then combustible. Which means the smaller molecules are the ones that are actually taking part in the combustion process. It is further stated that if PMMA decomposes in an atmosphere without oxygen, most of the product is the monomer, but not completely. There are other components that are being released besides the monomer. The TGA experiments that we are looking at have been performed in inert atmosphere. The same is true for the MCC. The pyrolysis is taking part under nitrogen atmosphere. It is pointed out here that next to the monomer also carbon dioxide and methane are being released. There are many intermediate species that are involved in the decomposition process. For the gas mixture that I want to use in the simulation, I have picked methane, ethylene and carbon dioxide to keep it simple. Since all 3 components are already implemented in FDS, I can just directly use them here. All 3 components are then combined into a new species, which is called the fuel mixture. You see here I've set already up the placeholders for the different volume fractions. Then I connected the fuel mixture to the combustion reaction and also added a soot yield. Now all the decomposition reactions and the material definitions need to be adjusted so that they are releasing the fuel mixture. For the gas mixture, I am now using the parameters with dependencies. The primary reason is that I want to have all the components add up to 100%. At first we will pick a random value between 0 and 1. This is the fraction for the first component, which I have called here A1. The float values that I've put in here are supposed to be the gas values from the optimization algorithm. So the second parameter will then be a fraction of whatever is left over after the first fraction is subtracted. Right, so we have 100% minus the first fraction, and whatever is left over, the fraction of that will be the second parameter. Then the third parameter will have an even smaller space to live in. From the 100%, I subtract now the first and the second parameter, and then take the fraction of whatever is left over. This process is then repeated for however many components we want to use, minus 1. This is because the last parameter will just contain what is left over. And as a check, if you were to add up all the components that we have set up above, the check value should add up to 1. Since our mixture contains 3 gaseous species, we just need to have 2 parameters and the last one will get whatever is left over. The first parameter here is a regular optimization parameter. Again, we give it a name, a placeholder, and then set the sampling range. The second parameter is a little bit different because now we need to use the helpers. The helpers allow us to evaluate a function, the result of which is then stored in the environment parameters. To set up the second component, we start from the 100% and subtract the CO2 fraction. With the helper, we determine the fraction of whatever is left over. This will be then methane. The helper itself is a regular optimization parameter. The final component is just the remainder, so we start from the 100% and subtract the other 2 fractions. Now the material mass fractions in the surface definition need to be adjusted. Since all the mass fractions are also supposed to add up to 1, we are again using the parameters with dependencies. And you see it follows the same strategy. For the first component we pick a random value between 0 and 1. For the second component we take a fraction of whatever is left over from the first step and then go into the next step and so forth. After all the optimization parameters have been defined, they are collected here in a parameter set. Now it's time to provide more information on the simulations. First, we start with the MCC simulation. This simulation definition is the beginning of our simulation setup. Since the parameters for the material definition won't change, we can just provide them here as a parameter set. To label the simulations, we provide the character ID. This is essentially an environment parameter. For this label, we need to provide an appropriate placeholder. Furthermore, we add in the parameters with dependencies and the environment parameters. Let's set up the first relation to connect the experiment data with the model response. At first, I would like to have the simulation match the heat release rate from the experiment. With this, I mean the actual heat release rate plot over temperature. Again, we call another data object from PROPTI, this time the relation. This first relation is initialized and assigned to the variable R1. Next, the relation will get a label. This is similar to the name of the parameters that we defined before. Next, we will define the file name that will contain the model response. In our case, FDS will create the _tga.csv file, and we are using the character ID to label the file. Within this file, PROPTI is to look for two data series. The X values are the temperatures and the Y values are the MCC data. We also define the header line, which is the line in the CSV file that contains these two strings. Let's have a brief look at one of these TGA files that are produced by FDS. The first line, line 0, will contain the units for each column. The second line contains the column headers. Following the Python numbering scheme, this would be line 1, and therefore here the header line is 1. In this header line, we are then looking for the temperature column and the MCC column. The keen observer may notice here that this looks very similar to how you use pandas data frames. The reason is that we internally are using pandas data frames. Now we are doing the same procedure, but this time with the experiment data, which is our target. Note here the switch between model and experiment. From the previous video we know that the file structure is slightly different, so the header line is here line 0. Opposed to FDS, in the experiment data the temperature is provided in Kelvin instead of Celsius. Therefore we are implementing an offset here to transform the temperatures to Celsius. Finally, we need to provide a fitness method that is to be used with this particular relation. In this case we are using a simple root mean square error. N point sets the number of points to which the X values of both data series are interpolated. This is necessary because the root mean square error checks for the differences in the Y-axis. Furthermore, we are setting the scale fitness value to true. Next, I'm defining a second relation. Note here that the variable name is R2. The second relation is used to determine the heat of combustion. Note also that I'm now looking for different X values for the data series, the time. Also a different fitness method is used. This time we are integrating over the data series. This fitness method is provided with a parameter, the integrate factor. With the integrate factor I'm determining how much of the material released is gas, and from that gas I would like to have the heat of combustion. Therefore it's 1 minus the residue fraction. Now it is time to collect all the information from above into a simulation setup. Again, this is a data structure that we can call from PROPTI. The simulation setup needs to be given a name, and I'm also using the character ID I used for the MCC simulations. The next parameter defines a working directory, which is used by PROPTI to store the information related to the simulations. For convenience, I'm using the same character ID. For convenience, we can also add an execution directory prefix. In this case, we are using the temporary directories on the worker nodes in the supercomputer. This helps with cleaning up the data in case PROPTI crashes. Next, the file name for the simulation template file is provided. Now we also need to add in the set of parameters that we have defined above. This includes the optimization parameters as well as the environment parameters. Now the model executable needs to be provided, which in our case is FDS. This entry looks a little bit convoluted here, but in principle it is just calling FDS. We have wrapped this call into a shell script, which I will explain later on. Finally, a list with the different relations is provided that we have defined above. So with the simulation setup of the MCC, we have now seen how we can compare multiple data series from the same simulation with different targets. Now we will expand on this by adding another simulation setup. This simulation setup allows us to compare the parameters in completely different conditions. In this case, we want to reproduce a TGA. This means in the end we have a parameter set that will be used in two simulations in parallel, the MCC and the TGA. You will find that the setup itself is basically the same as we just did. We begin here to define a new TGA simulation setup. For this we create a new parameter set and assign the same optimization parameters as before, because our material parameter set stays the same. We are then adding a different name for this parameter set, in this case it's the character ID of the TGA. Again we are adding in the environment parameters as well as the parameters with dependencies. We create a new relation and give it a proper label. We set up where to find the model response, as well as what experiment data is to be used. We again use the fitness method RMSE because we want to match the whole development. This time we provide a range to just look at the subset of the data. Note also that I've assigned a fitness weight here, which allows us to give more weight to this specific setup. The reason is that PROPTI will provide a fitness value for each of the relations, so that means we have 3 fitness values here. These 3 fitness values will be summed up, and the sum is used by the Optimiser to be minimized. Let's have a brief look in the database file that PROPTI will produce. The first couple of columns are labeled like 1, like 2, up to like n. In these columns, PROPTI writes the fitness values. Like 2, like 3 and like 4 in our case are associated to relation 1, 2 and 3. Looking in the first line, the like values 2, 3 and 4 summed up should be the same as like 1. Due to the summation, the MCC would have a higher impact. This is what I am trying to mitigate by using a fitness weight with a factor of 2. All the information related to the TGA simulations is then also collected in the simulation setup. Next, both simulation setups are collected in the simulation setup set. This is another data object that we can directly call from PROPTI. After the simulation setup set is initialized, both setups will be added. For convenience and also to reduce errors, I am determining here the number of parameters that are optimized. This is based on the list that we have set up above. Lastly, we need to provide information for the optimizer. The optimizer properties are again a data structure from PROPTI. First, we define which algorithm we want to use. In this case, it's the shuffle complex evolutionary algorithm provided by SpotPy. Next, we set the number of repetitions. This is the amount of individual parameter sets that are to be considered within this inverse modeling run. This is one of the termination criteria. If this number is exceeded, the IMP run is stopped. The backup every parameter defines the interval with which save points are created. In the case of the shuffled complex evolutionary algorithm, every save point can be written only after a generation has been completed, which means PROPTI will create a save point after every generation. This parameter is comparable with the DT restart in FDS. With NGS, we set the number of complexes used by the shuffled complex evolutionary algorithm. In our case here, we have the same number of complexes and optimization parameters. This parameter enables PROPTI to start subprocesses. These could be used to run multiple simulation setups in parallel. However, in our case, we are using the TGA analysis functionality in FDS. These simulations run very fast. In this case, it is not necessary to have the simulation setups run in parallel. However, we will set the MPI parameter to true. This allows PROPTI to run at least the complexes in parallel. Finally, we set the max loop increment. In the case of the shuffled complex evolutionary algorithm, this means how many successful generations are to be completed before PROPTI is gracefully stopped. When using supercomputers, you can typically book only limited time frames for each single job. With the max loop increment, we can ensure that PROPTI can stop on its own terms instead of being killed by the system. I have also copied the MCC template and renamed it to the TGA template, as well as added in the appropriate placeholder for the character ID. Both files are for the most part identical, just note that the heating rates are different. For the MCC template, the heating rate is set to 60 Kelvin per minute in the surface definition. In the template for the TGA simulation, however, the heating rate is set to 50 Kelvin per minute. These are the two heating rates of the experiments that we want to match. With this now, the initial setup of the PROPTI run is completed. In the next video we will then discuss how we run these jobs on the supercomputer. Have a nice day and see you in the next video.